Hey everyone, and welcome back to The Explainer. I've got to say, I am incredibly excited about today's topic because we are looking at something truly mind-bending. We're going to explore the absolute bleeding edge of human knowledge. In 2026, the mathematics world awarded its highest honor, the Fields Medal, to four brilliant individuals who have literally rewritten our understanding of reality. We are talking about translating the chaotic bouncing of atoms into predictable fluid laws, finding zero-volume spaces where physical waves can actually travel, counting the invisible dimensions of string theory, and using pure logic to tame these totally wild mathematical structures. It's a fascinating journey, and as always, we are going to make it crystal clear. Okay, let's dive right into this. Here is our roadmap for today. We'll start with number 1, the Nobel of Mathematics. Then 2, chaos and fluid laws. 3, spinning needles and waves. 4, counting invisible dimensions. 5, logic in number paths. And finally, 6, a unified mathematical tapestry. All right, section 1, the Nobel of Mathematics. So, you've probably heard the Fields Medal called the Nobel Prize of Mathematics, right? It's given out only once every 4 years by the International Mathematical Union. But here is the real kicker. It is only awarded to mathematicians under the age of 40. This isn't just some lifetime achievement award for a long, winding career. It's a massive recognition of explosive, extraordinary achievement and the promise of what these brilliant minds are going to discover next. The winners receive a gold medal bearing the face of Archimedes, along with about $10,600. But the true value, of course, is the prestige. It is widely considered the absolute pinnacle of mathematical achievement. And this brilliantly illustrates the caliber of our 2026 laureates. Just take a look. We have Deng from the University of Chicago, specializing in partial differential equations. John Pardon from Stony Brook University, working on symplectic geometry. Jacob Tsimerman from the University of Toronto, focusing on arithmetic geometry. And Hong Wang from NYU and IHS, a total master of harmonic analysis. That's 4 different institutions and 4 vastly different primary research fields. But as you'll see, they are all essentially picking the locks on the exact same universe.
Moving on to Section 2, Chaos and Fluid Laws.
You really have to look at the fascinating trajectory of Yu Deng's life. Born in China and raised by a software engineer and a gastroenterologist, Deng exhibited this intense strategic thinking really early on. He actually competed professionally in the Chinese board game Go. But at age 16, he pivoted fully over to mathematics and ended up winning a gold medal at the International Mathematical Olympiad. That strategic, puzzle-solving mindset, managing infinitely complex possibilities on a board, it perfectly primed him for his eventual destination, tackling some of the most complex, chaotic, partial differential equations in physics as a full professor at U Chicago.
Deng's breakthrough is incredibly profound. Way back in the year 1900, the mathematician David Hilbert proposed this famous list of problems, and his 6th problem basically asked if we could derive the macroscopic laws of physics strictly from microscopic first principles. Well, Deng took this on. He rigorously derived the Boltzmann equation from what's known as hard sphere dynamics. To translate that into plain English, he mathematically proved that if you have billions of microscopic particles just crashing into each other in total chaotic randomness, over long periods of time, those crazy collisions naturally smooth out into the highly predictable laws of fluids and gases that we actually observe in the real world. He literally built the mathematical bridge between microscopic chaos and macroscopic order. That brings us to Section 3, spinning needles and waves. Now, Hong Wang made history as the 3rd woman and the first Chinese woman ever to win the Fields Medal. To understand her work, we have to look at a brain teaser proposed way back in 1917 called the Kikaya problem. It asks, how much space does it take to turn a needle 180 degrees so that it points in every possible direction? So the crucial point is, we are not spinning it a full 360 degrees in a circle. We just need it to reverse its orientation exactly 180 degrees, allowing it to point everywhere. In 2 dimensions, you can cleverly slide and rotate this needle in a remarkably tiny, almost non-existent area. But when you move this whole concept into 3 dimensions, the math breaks down and gets incredibly difficult. It's wild to think about, but Hong Wang completely cracked the 3-dimensional Kikaya conjecture. She proved that you can actually build a highly fragmented, fractal-like space that allows this needle to spin in every direction, even if that space has a physical volume of 0. 0! But, and this is the absolute genius part, even though it has 0 volume, it cannot be compressed below 3 geometric dimensions. Why does this matter to us? Because this completely paradoxical mathematical space perfectly models how overlapping physical waves, like light and sound, disperse, interact, and smooth out over time in our universe. It is a massive leap forward in harmonic analysis. Let's move on and see how this builds because it's a perfect pivot point. Our first two medalists, Deng and Wang, gave us the math to understand our kinetic physical reality, right? Fluids crashing and waves dispersing. But now we're going to pivot to the structural truth of the universe. We're talking about the hidden geometry, the invisible dimensions, and the pure logic that props up our reality as decoded by our next two laureates. Section 4. Counting invisible dimensions. Now, what's really interesting about this is how it ties into quantum physics. In superstring theory, quantum physicists model our universe with 6 hidden microscopic dimensions wrapped up into incredibly complex shapes called Calabi-Yau threefolds. To understand these shapes, mathematicians had to count the curves within them. But there was a massive problem. They had 2 completely different mathematical methods for counting these curves, and nobody actually knew if they were compatible. This was known as the M&OP conjecture. Well, John Pardon built a reliable, robust mathematical toolkit to execute these counts. He definitively proved that both methods yield the exact same answer. He quite literally secured the mathematical foundation for how we model the hidden dimensions of quantum physics.
Next up, Section 5, Logic in Number Paths.
When we talk about arithmetic geometry, it sounds incredibly abstract and isolated, doesn't it? But Jacob Tsimerman has such a great perspective on this. He says, math is such a team sport that it becomes impossible to disentangle who contributed what on projects. I'm lucky to have many of my collaborators as close friends. He's actually famously known at his university for hanging out in the lounge, happily puzzling over complex equations on a blackboard with his students. And honestly, this deeply collaborative human approach is exactly how he conquered one of the most stubborn problems in number theory. So let's break down his highly technical breakthrough into plain English. Tsimerman solved the decades-old Andre Oort conjecture. To do this, he borrowed a concept from the highly abstract field of mathematical logic called O-minimality. Basically, in complex geometric spaces, special points of numbers can sometimes scatter in wildly unpredictable, chaotic ways. Tsimerman used this logical framework of O-minimality to essentially tame these wild structures. It is honestly mesmerizing to think about. He proved that when these special coordinates appear in large numbers, they don't scatter randomly. Instead, they are forced to form orderly, structured geometric paths. He essentially proved that there are hidden logical guardrails governing how numbers behave on geometric surfaces.
And finally, Section 6, a unified mathematical tapestry.
We so often think of science as these isolated, fragmented disciplines, but look at how beautifully these 4 fields connect. On one side, we have the microscopic and physical world. Deng's work showing how chaotic particle collisions create the fluid laws we experience, and Hong Wang's work showing how overlapping waves of light and sound disperse through paradoxical zero-volume spaces. And on the other side, the macro and the conceptual. John Pardon unlocking the dimensional limits of string theory by counting curves, and Jacob Tsimerman proving that fundamental logic actually tames wild number chaos. Together, they prove that whether you are looking at the smallest colliding atom or the absolute widest conceptual geometry, our universe is bound by a profound, beautifully discoverable order.
Which leaves us with a final, highly provocative thought. If modern mathematics, driven by these brilliant young minds, can mathematically tame microscopic chaos, map out zero-volume wave spaces, and decode the invisible dimensions of string theory, what other fundamental secrets is our universe still hiding? We are really just scratching the surface of reality here, and the math is leading the way. Thank you so much for joining me on this explainer. I hope this helped you see the incredible structure of our world just a little bit more clearly. Keep wondering, keep learning, and I'll see you next time.